Here I go again with topics that I'm not an expert on, but I read them because they are important, as I always say, and I tell you about them because I think they are exciting. And if you're an expert, you are a chemist, or you are a person who does these organic frameworks. We have talked about metal organic frameworks before. This one is about a covalent organic framework. For capturing CO2, metal organic frameworks are used for various purposes, even like fog harvesting and so on. You can look them up. So, what is this about? Carbon dioxide capture from open air using covalent organic frameworks. I know enough chemistry know that covalent means there are atoms that are sharing electrons in a bond. So capture of CO2 organic frameworks basically are some crystal structures or some molecular structures that allow, it's a porous media that has properties of adsorbing things, and then you can desorb them. So if you adsorb CO2, then you can desorb it and then take it out. So you are flowing air through this covalent organic framework, and it's absorbing CO2, sticking on the surface, and then you can desorb it. Okay, in a simple way. Capture of CO2 from the air offers a promising approach to addressing climate change and achieving carbon neutrality goals. This is why I always look these up. However, the development of a durable material with high capacity, fast kinetics, and low regeneration temperature for CO2 capture, especially from the intricate and dynamic atmosphere, is still lacking. CO2 concentration is very low, 0.04%, 440 or 427 ppm or whatever it is now. Will keep increasing, but it's very, very small, which means you'll have to flow through a lot of air to capture this tiny amount of CO2 that's in there. One method uses precipitating out, so some reaction catalysis that takes CO2 into some solid form and precipitates it out, and here you are absorbing it, and you need to desorb it, as I said, which means some temperature, heating, etc. will be involved. Here a porous crystalline covalent organic framework with olefin linkages has been synthesized, structurally characterized, and post-synthetically here goes my throat again, post-synthetically modified by the covalent attachments of amine initiators for producing polyamines within pores. A lot of chemistry there, I agree, but olefin linkages, so crystalline covalent organic framework has olefin framework, literally, you can imagine. I won't show a figure, but the paper has a nice figure you can look up. And olefin, so amines are always used for CO2 capture as well. So you can look up the chemistry, as I said. This COF, or covalent organic framework, called COF 999, can capture CO2 from open air. COF 999 or 999 has a capacity of 0.936 millimole per gram under dry conditions and 2.05 millimole per gram under 50% relative humidity, both from 400 ppm CO2. So they have set a background level, dry air, moist air, because the framework does, I guess, together water vapor and CO2. This, obviously, CO2 is highly soluble in water as well. This COF was tested for more than 100 adsorption-desorption cycles in the open air of Berkeley, California, and found to fully retain its performance. So field experiments have been done. COF 999 is an exceptional material for the capture of CO2 from open air, as evidenced by its cycling stability, so you want to be able to use it in multiple cycles. Facile uptake of CO2, which reaches half capacity in 18.8 minutes. So it has a certain full capacity. What's the half cycle time it takes? 18.8 minutes for the airflow, and low regeneration temperature at 60 degrees C to desorb the CO2, so that is always useful. Here is a figure. I'm jumping ahead and showing just one figure of the air experiment in the real world. Carbon dioxide capture from open air, CO2 capture productivity after each adsorption cycle in blue here. So you can see the operating time of the day and CO2 productivity in millimole per gram, in the range of what we mentioned before, depending on humidity. Berkeley, California is a relatively dry place. It's along, cold region, cooler region of California. It's in the interior, but still. And that's blue. Corresponding ambient outdoor CO2 concentration in red. You can see it's locally during the day, it's at the global level, plus some spikes you get from local pollution and so on. It's a well mixed gas, but you have to measure it away from local activities to get a good sense of the global concentration or hemispheric concentration. And RH, relative humidity, is black. You can see it's relatively dry, typically less than 50%, with some drier spikes going down to 30% relative humidity, which probably means there are breezes which are onshore, offshore, and so on and so forth. CO2 productivity of selected cycles with an ambient RH of 37 plus minus 1%. So cycle number, CO2 productivity in millimoles per gram. Background CO2 concentration is also given in red. Background relative humidity is around 37. So these are probably lab experiments, or let's see, with corresponding ambient outdoor CO2 concentration. Obviously that means they are not doing it outdoors. Average productivity of selected cycles is shown as the dotted line. So that's here at 1.2 something millimole per gram per cycle. C is the comparison of single component CO2 sorption isotherms. So obviously you have adsorption happening, and desorption has to happen to heat up the framework to release the absorbed CO2. So those details are given here in terms of CO2 uptake in millimoles per gram with absolute pressure, which always matters as well. So as synthesized and after 100 cycles, so in near real time versus waiting after 100 cycles. So you can see that the adsorption and desorption, so you can see the amount of uptake happening millimoles per gram as synthesized, and after 100 cycles the performance doesn't degrade. So this is C over C0, where C0 represents the absorbed concentrations in the downstream and upstream gas flow in the experiment. Okay, so basically they are saying they have run it for this is 10 hours, and the performance picks up and then it remains steady or reaches a maximum. So just to jump ahead, let's read a little bit about the chemistry just for fun, because you will see I won't even be able to pronounce many things properly because they are deep chemistry that I don't know anything about. A porous crystalline olefin linked CO-COF precursor, COF 999N3, was first synthesized throughout Novenagel. Okay, I told you I won't be able to. This says Knoevenagel, Novenagel, I suspect, because K must be silent. That's a condensation process between 3.3. Okay, that's too much chemistry. Let's not do it. Let's just say there are details there. Okay, I tried. Okay, we have shown how COFs with an olefin linked backbone and covalently attached sorption sites bringing ultra high chemical stability can serve as excellent materials for capturing CO2 from the air, which is what I'm most interested in, because if we want to get to net zero 1.5 to whatever we are going to reach by 2100, carbon capture has to be part of the portfolio of solutions, and there will be irreducible emissions which will have to be taken out. We call them negative emission technologies and so on. So I try to track the exciting research in carbon capture directly from the air or into the ocean or whatever So we have to just read through these, and it's okay that if we don't understand the detailed chemistry necessarily. Our studies demonstrate that this application in the open air is a marked advance towards achieving clean air. It's also clear that the present COF 999 is perhaps one of the first members of what we believe will be a large class of materials with a robust framework backbone that we expect will serve the general purpose of carbon capture very well. So you can imagine you will have artificial trees with this. Artificial trees already exist. I think Gary Lackner, if you can look it up, who keeps doing that, and his problem has been to reduce the size, because per millimole per gram of CO2 capture, how big does the tree have to be? Real trees do it all the time, but they have a lot of leaves, so they have a lot of frameworks in which they are doing this. Okay. It's also clear that present COF 999 is perhaps one of the first members, as we said, but these large class of materials with a robust framework backbone will serve the general purpose of carbon capture very well, according to these authors. By applying this strategy, other reticular structures will have to be designed, examined and compared as well with COF 999 to further improve the capacity and performance. In the meantime, the scalability of this COF and the design of a practical device will be an important priority for future implementation of these materials. So technology readiness level is low. Outdoor demonstration has been done, as we saw here, so it looks promising. How does it scale up? How much will be its capacity, energy use, life cycle analysis kind of thing? We will see, but right now, let's say reticular has to be a shape that we are interested in. So reticular is characterized by a fine network or net-like structure. So that's the organic framework we are talking about. So I'm going to just leave it there. Brief, just as far as possible. Learn from these, keep track of what's happening, and look up more details if you want. It has nice background material references and references to other methods which use similar approaches of, similar methodologies for, not even methodologies. Basically, a lot of people are trying DAC, right? Direct air capture, as we said, precipitation, climb works and so on, which are implementing, already being deployed in the field and so on and so forth. So let's leave it here.